Solomon codes. Let's start with the basics of error correction. Intuitively, how do we do error correction when we communicate in day-to-day life? Let's say I want to communicate a message 010 to you. If I were to just send the message 010, maybe some bit gets flipped due to noise, and that would completely change the meaning of this message. What we do usually is to replicate the message, let's say 3 times now. And then if this replicated message, all 3 of them are sent, then even if there is some noise, let's say this bit got flipped from 0 to 1, even then you can look at the first and third copies and infer that the original message was 010. Likewise, if this bit got flipped, then you can look at the first and second copies. So really, by making 3 copies, we can make this communication resilient to one error. And this is the basic mantra in coding theory, that we add redundancy and gain robustness to errors. Okay, let's formalize this mathematically a bit. An error correcting code is just a subset of sigma to the n, where sigma is some finite alphabet. So the code can be seen as a collection of n-length strings. How is this code used? Let's say we have a k-length string. Think of k as being smaller than n. Then this k-length string is encoded to an n-length string, let's say y. And when this y is passed through a noisy channel, it will get corrupted to y tilde. And the hope is that the code should be designed in a way that, given access just to y tilde, we should be able to recover what y was. And this is through a process called decoding. So this is the task of decoding. The code C is called linear if it is not just a subset of sigma to the n, it's a subspace. And for this, we want sigma to be identified with a finite field, let's say fq. The 2 most important parameters of a code are its distance and rate. The distance is minimum normalized Hamming distance between any 2 distinct elements, any 2 distinct strings in the code. So this distance is going to be a fraction between 0 and 1. Let's say it was 0.2. That means that any 2 distinct code words differ in at least 20% of the positions. And the rate is this ratio k over n. We started with a k-length string. We encoded it to an n-length string. What is the ratio k over n? That's a measure of how much redundancy we are adding. Okay. Let's just do this pictorially once. Let's say this is the ambient space sigma to the n. The code will look like a subset of this space. And the distance is meant to ensure that any 2 code words are separated from each other. And let's say we have this code word y. If y was corrupted by the noisy channel to y tilde, as long as this corruption was not too much, as long as the corruption was, let's say, under delta over 2, then we can at least theoretically map y tilde uniquely back to y. That's because all these Hamming balls of radius delta over 2 are disjoint from each. Okay, so large distance is supposed to facilitate decoding. Okay. Codes have a lot of applications. They were originally designed with practical applications like communication, storage, etc. in mind. Since then, we've also come to understand them as a fundamental pseudo-randomness primitive. That's because really a code is a well-separated set of large size. If we want properties like this, random sets do really well, but explicit constructions tend to be hard. And a lot of explicit constructions can be reduced to just designing the right code, maybe with some extra special properties. And codes by now are ubiquitous in theoretical computer science. There are connections to average case hardness, communication complexity, PCPs, etc. And in particular, for these applications to pseudo-randomness and average case hardness and complexity theory, it's really important that we have codes that can correct a large fraction of errors. So let's see how large we can make this fraction of errors. So there's properties of well-separatedness and being of the set being large size. There is an inherent tension between these 2 parameters, because the rate is measuring how dense the set is and distance is how well separated it is. And the most basic bound that captures this tension is called the singleton bound, which says that the sum of rate and distance cannot be more than 1. Okay. This means that if we have a rate R code, the distance has to be at most 1 minus R. Right. So any code must satisfy this inequality that the rate plus distance cannot be more than 1. But this doesn't rule out, let's say, constructing codes with distance as close to 1 as we want. Do there exist codes with such parameters? And indeed they do. They're called the Reed-Solomon codes. This is probably the most well-studied family of codes. These are based on bounded degree polynomials over finite fields. So think of f as a degree Rn polynomial over fq. The code word is just evaluations of this polynomial at n distinct points. So alpha 1 through alpha n are points in the field, and we are evaluating the polynomial over these distinct points. Okay, let's look at, so just to go into more detail about this, let's say k is equal to Rn. Then degree Rn polynomial is going to, can be seen as a message of length k, or a string of length k over fq. And these k symbols can be seen as the coefficients of x to the I. So every k length string can be seen as a degree k polynomial over fq. Okay. And the encoding of the k length string is just evaluations of the polynomial over n distinct points. Each of those evaluations are also in fq. So that's going to be a member of fq to the n. The rate, again, is just ratio k over n. We chose k to be Rn, so the rate is just R. What about the distance? So polynomials have this really nice property that if we have any two degree k polynomials, they cannot agree in more than k positions. They cannot. That's because otherwise the difference polynomial will have too many roots. Okay. This means that any two degree k polynomials must differ in at least n minus k positions, which means the distance is going to be at least n minus k over n, which is 1 minus R. So we saw that 1 minus R is the best we can do. Reed-Solomon codes give codes that are codes that achieve this trade-off. And they're really nice codes. We can correct half of the distance, many errors in near linear time. Reed-Solomon codes are used in a lot of places, from deep space communication to CDs to QR codes. One of the main drawbacks of Reed-Solomon code is that the alphabet size is too large. So remember, we needed n distinct points in the field to evaluate these polynomials on, which means that fq needs to have at least n points. So the alphabet size needs to grow with n. However, Reed-Solomon codes can be used for constructing binary codes via something called concatenation, and not go into too much detail about that. In fact, that these large alphabet codes are the preeminent ways of constructing binary codes. But another barrier that we can see from here is, can we correct errors beyond 50%? Because right now we saw that we can only correct half of 1 minus R many errors. So even if the distance is very close to 1, we can only correct 50% errors in the best case. And correcting errors beyond 50% turns out to be really important in these pseudo-randomness complexity applications. And of course, okay, let's, and the answer to correcting errors beyond half is something called list decoding. When the number of errors exceed delta over 2, then the corrupted code word could really sit between two different code words, and it's impossible to map it back uniquely to a code word. But the hope is that the number of code words in that radius is still polynomial, if not 1. So we can't go for one code word, but maybe we can go for a few. If it is exponential, then it's quite useless as a definition. But let's say we target a polynomial size less. And that hope turns out to be true. There is this classic result called Johnson bound, which says that there is always a threshold between delta over 2 and delta, up to which the list size is bounded. And for delta being 1 minus r in the regime of Reed-Solomon codes, this threshold turns out to be 1 minus square root r. So by making r small, we can correct errors that are arbitrarily close to 1. And this fact has had a lot of applications in different areas. And the list decoding problem also has an associated algorithmic task, which is to find this list in polynomial time. Okay. Just to illustrate this point a little more, this was the Johnson bound. What we are saying is that if we are drawing balls around a corrupted code word, up to delta over 2, we know that there can only be one code word. But up to j of delta, the Johnson bound radius, the number of code words cannot be too many. Maybe there are 4 new code words that came up, but not much more than that. Okay. And in a lot of applications, it turns out that uniquely recovering one of the code words is not as important as improving the errors corrected. Okay. For Reed-Solomon codes in particular, we can efficiently find this list. And this was due to this very influential work of Guruswamy and Sudan in late 90s. Okay. So if we look at the curve of 1 minus square root r, so the lowest curve is, this would be the unique decoding radius, this is the singleton bound, and then this curve is between them. And in the regime when r is small, really close to the best we can do. So it's not too difficult to show that just because of the singleton bound, we can't hope to correct more than 1 minus r errors. We have to be under the 1 minus r bound. But Johnson bound says that in this area also we can correct errors. But there's still this gap between 1 minus square root r and 1 minus r. The 1 minus r threshold is called the list decoding capacity. And do there exist codes that can correct as many errors? The answer is yes. In particular, random codes or random linear codes can correct as much as, so a rate r random linear code will correct 1 minus r minus epsilon errors for any epsilon that we want. These are, of course, non-explicit, and there's very little structure. We don't expect these to come with associated algorithms. And for Reed-Solomon, we saw that getting list sizes that are 1 minus square root r, getting list decoding radius up to 1 minus square root r is just a consequence of Johnson bound. And the results of Guruswamy and Sudan say that this can be made algorithmic. Then for a while, it wasn't clear whether we can construct explicit codes that truly get to the capacity of 1 minus r, until in 2006, Guruswamy and Rudra constructed this code called folded Reed-Solomon code, which can list decode up to 1 minus r minus epsilon. And later on, there were other codes also, which are also closely related to Reed-Solomon codes called multiplicity codes or univariate multiplicity codes that can correct the optimal number of errors. Okay. But until now, when I say list decoding radius, what I mean is that the list size should be polynomial in n, should be better than exponential. That's pretty much it. The alphabet size is, you mean for folded Reed-Solomon? So for random linear codes, we can do this with constant alphabet size depending on epsilon. For most of the explicit constructions, these tend to be depending on n, but there are expander-based constructions that will reduce the alphabet size to constant. In most cases, these expander-based constructions can reduce the alphabet size. In fact, in the original paper of Guruswamy and Rudra, they already gave a construction that was also over constant alphabet. List size turned out to be much more tricky. For binary, we are very far from any explicit construction. Most of the constructions we know are random. Random works for everything. Yes. In fact, the best binary codes we know are by using Reed-Solomon list decoding, by using concatenation. Okay. So what are these folded Reed-Solomon codes? Well, recall that for Reed-Solomon codes, we had message represented as the coefficients of a polynomial, and then the code word was evaluations of this polynomial. The folded Reed-Solomon code just groups together different evaluations. Let's say I'm talking about 3 folding, then it will group together 3 different evaluations and call them a single symbol. And in general, I can talk about M folded Reed-Solomon codes, which would be grouping together M different evaluations. And in most of the proofs that we will talk about, it is important that this folding is done along a particular structure. In particular, we'll have gamma to be a primitive element of the field. And then the folding needs to be in this particular order. That 1 gets folded with gamma, gamma square, and so on. So this process is called folding. How does folding a code affect its parameters? Let's say rate, distance, list decoding radius, all of these. First, it's not very hard to see that the rate is unchanged in folding, because rate was defined to be this, the number of code words log base the alphabet size divided by n. So when folding, the alphabet size increases and the block length decreases. So these factors will cancel each other. The rate is exactly the same. We are really transmitting the same amount of information, just interpreting it differently. The distance cannot decrease, but it may increase. But if we are talking about optimal codes to begin with, it cannot increase even more. Otherwise, we would be violating the singleton bound. So at singleton bound, even the distance remains. Again, the list decoding radius cannot decrease. But it turns out that for folded Reed-Solomon codes, we can prove things that we don't know for Reed-Solomon. So this 1 minus square root r versus 1 minus r kind of discrepancy. The best known list decoding radius for Reed-Solomon still continues to be 1 minus square root r, but for folded Reed-Solomon, we can do better. We just don't know how. There's some evidence that says that, but there's no formal proof. Yes, so for random evaluation points, we know that even Reed-Solomon will achieve capacity, but for arbitrary evaluation point, we do. Okay. Okay. So now let's talk about the list size. And the main theorem, which was a simplification of the original Guruswami-Rutra result, says that if we are talking about M-folded Reed-Solomon codes, then there is some threshold. Let's say we ignore this factor for now. By increasing M, this can be made arbitrarily close to 1. So what we are saying is that up to k over k plus 1 times the distance, the list is going to be contained in an affine subspace of dimension k minus 1. So we are getting closer and closer to the distance, but the list is always contained in an affine subspace, which immediately means that the list size is at most q to the k minus 1. And q is generally taken to be roughly n. So this means that the list size is n to the k minus 1. Okay. We'll see this factor again, but really you should always think of this k over k plus 1, 1 minus r. So this means, for example, if we were to choose k to be 8, we can get 8 over 9 close to the distance, 8 over 9 factor away from the distance with the list size of n to the 7. And if we were to choose k to be roughly 1 over epsilon, then we can get 1 minus r minus epsilon with a list of size n to the 1 over epsilon. So if our definition of list decoding capacity is polynomial size list, this says that we achieve list decoding capacity. But this list size of n to the 1 over epsilon is not very ideal. In particular, random codes definitely beat this kind of bound. So we'll see. For random codes, the list size turns out to be just 1 over epsilon when we are decoding at 1 minus r minus epsilon. For folded Reed-Solomon codes, as I just said, the list size is n to the 1 over epsilon. The first three constructions are random. All the later ones are explicit. And then with a view to reduce this list size, there was a construction, explicit construction of something called subspace evasive sets by Dweer and Lovett, which was able to reduce the list size to 1 over epsilon to the 1 over epsilon. So it is a constant independent of n. So as n goes to infinity, this still remains the same. And later, it was found that even without any modification for folded Reed-Solomon codes, the list size is a constant independent of n, just by an improved analysis. And this analysis just says that we already knew that the list is contained in an affine subspace. Affine subspaces and Hamming balls do not interact very well with each other. So any affine subspace, not all of it can be contained in a Hamming ball. And so until this work, the best known list size continued to be 1 over epsilon to the 1 over epsilon for capacity achieving codes. And in this work, we show that the list size without any modification to folded Reed-Solomon is just 1 over epsilon square. We'll see more of that later in the talk. The folding is always the same folding. Yes. Yeah, so mostly, I think there are generalizations that there can be additive folding instead of this multiplicative folding. Recently, there was some work on affine folding, but not necessarily using expanders. Yeah, so all of these results, except for the subspace evasive ones, are just for the folded Reed-Solomon itself, without any modification. Okay. 1 over epsilon is the best we can do. And the result that we show is actually more fine-grained. We say that for any k over k plus 1 fraction of the distance, we get a list size that is just k minus 1 square plus 1. So even for small values, let's say 4 over 5, this will give a very benign list size of 10, or up to 8 over 9, it would be 50, so on. To compare, like with these kind of fixed k, not much was known before. The best we could do was n to the k minus 1. So we'll talk about this k over k plus 1 decoding in 4 rounds. Let's say we start with the first round, which is, so the definition of this L is just all code words that are close to some f tilde. By close, I mean k over k plus 1 times delta. In the first round, let's say the list was contained in a one-dimensional affine subspace. And in this case, we'll show that the list is just going to be of size k plus 1. Can't be more than that. Okay. So one-dimensional affine subspace can be seen as just a line, h0 plus t times h1, where t is varying all over the finite field. And what does this affine subspace look like? So our only candidates for the list are going to be in this subspace. And we just have to pick out which t's work for us. Let's write down the subspace for different values of t. For t equal to 0, it's just going to be h0. Let's say it's some evaluation of a polynomial. These are not necessarily low degree polynomials, but just numbers that I came up with. For t equals 1, some values will change, some will not. And it depends on h1 being 0 or not. So let's say the first position h1 was 0. Then the first position will remain unchanged. Same for the second one. For the third one, let's say h1 was 1. That would mean that the position changes. Likewise, for the fourth position, h1 was again non-zero. For all the remaining ones, let's say h1 is non-zero. So these values are all different from the ones on top, except in the first two positions. This is going to continue. In the first two positions, we are always going to have the same value coming from h0. In all the remaining ones, they are always going to be different. So really what we are saying is that in any of these columns, all the values are different. And in any of these columns, all the values are same. That just depends on whether h1 is 0 or not. Let me call this set S where h1 is non-zero. Okay. Any questions? So this is just writing down the affine subspace that are candidates for the list. The goal is to pick out T's that could be list elements for us, finally. Yes, yes. Which it might not. The code is same, the analysis is better. That's all. So it's just a combinatorial proof. The algorithm also remains the same. Yes, yes. Okay. So S is this set where h1 is non-zero, which means that these coordinates are varying. This set is going to be at least delta n because the code has distance. So the number of non-zero guys always have to be at least delta n, which immediately means that every code word in the list has to agree with f tilde in at least 1 over k plus 1 fraction of s. Because if not, then it disagrees in at least k over k plus 1 fraction, which is too much because eventually our budget is only k over k plus 1 times delta. Is this part okay? All we are using is that the set is of large size. Because h1 is a member of the code. So this one-dimensional affine subspace is of the code. Okay, maybe it should be clarified that this one-dimensional affine subspace is of just the code. It's not an arbitrary one-dimensional. Code words. Yeah, so this one-dimensional affine subspace is only for example of low-degree polynomials. So everything here is low-degree polynomial in particular. So these are all code words. Right, so this set is of large size, which means that the agreement has to be at least 1 over k plus 1. Again, if not, the disagreement will be k over k plus 1, and the set is large, so that would be too much disagreement with f tilde. And secondly, these agreement sets are all disjoint because if for one list element, let's say it agrees here, it cannot agree anywhere else here. That's the point of writing out these columns, that these are all different. So every agreement set is covering 1 over k plus 1 fraction. and they are all disjoint. So the best we can do is k plus one total number of agreement sets. Okay. So for example, for k equals 2, this says that the list has to be less than 3, has to be 2. And the other way of seeing this is that if we fix j to be an agreement, which means that we are fixing the value of jth coordinate in this line, then that fixes what t was as well. Because it's a line, so we can write this as h0j plus t times h1j equals gj. So overall, we use two things. One, that this set was large. That means that all these agreement sets cover a 1 over k plus 1 fraction, and that the agreement sets are all disjoint. And now we'll slowly start using this in an induction. This was the d equals 1 case. This will become the base case. Yeah. So f tilde is the received word. It's the corrupted word. That is always fixed. So f tilde here should be seen as the corrupted word. And then there could be two different candidates, f1 and f2. For those two, these agreement sets are going to be disjoint. So the agreement is always seen with respect to a fixed f tilde. In fact, like this subspace has already come with a fixed f tilde in mind. Uh, no, so I think being different comes in basically here that the set was large. So if you did not agree at all, then you would be too much different from f tilde. The second case, all I'm saying is that as soon as, let's say, 1 and 6 were an agreement set here, that means that the G was, sorry? Yes, exactly. Yeah. So the other agreement set will have to look in the last three coordinates. Yeah. Okay. This immediately means that, so L1 is the notation I'm using for one-dimensional assumption that the list was contained in one dimension. And we get that L1 is at most k plus 1. Okay. Let's put this aside. This is the proof for that we just did. And try to do a round 2 with just 2 dimensions. This will pretty much make clear what the induction is going to look like. So now the subspace will look like h0 plus t1 h1 plus t2 h2. T1 and T2 will both be free parameters. Again, we'll choose the set S to be anywhere where either H1 or H2 or both are non-zero. So what we really want to exclude is that both should not be zero. Again, this will mean that S is going to be large. In fact, just one being non-zero is already sufficient to say that S is large. And with the same argument as before, F is still going to agree with F tilde in S over K plus 1 position. So this just relied on the size of set S. The second property is more interesting because now we can't say that these are just disjoint. Two-dimension subspace is not going to have this nice structure. But it still is true that if we fix J to be an agreement, that is going to give a new affine constraint on T1 and T2. And this affine constraint is going to be non-trivial because we chose S to be, okay, this should be not equal to. So we get a new affine constraint, and then everywhere where a particular J is an agreement, that will really look like a dimension 1 case. And then we can say that previously each J was in at most one agreement set. Now we can say that each J is actually in at most L1 agreement sets. L1 is the list size for dimension 1. this is some sort of weak disjointness property that each vertex only appears in so many agreement sets. Okay. Is this okay? And then again, we do the same argument, we'll get that L2 is at most k plus 1 times L1. In general, we'll have this induction that LD is always going to be k plus 1 times LD minus 1. And with this, we can prove that LD in general is k plus 1 to the d. We can do a little bit better because all of these are strict inequalities. And then if we recall this theorem that list was contained in an affine subspace with dimension k minus 1, this says that list size is actually k plus 1 to the k minus 1. This is just plugging in what we already know. So if we choose k to be 1 over epsilon, this already recovers 1 over epsilon to the 1 over. Okay. Don't agree with each other. Right, right, right. Yes. Sorry. Sorry, I didn't get. Yes, yes. Yeah, so really what I'm using is Hamming balls that we are talking about agreement with some F tilde and a subspace. That's pretty much it. So this has nothing about folded Reed-Solomon or Reed-Solomon. This is just linear codes and Hamming balls and subspace. All we used was that we are talking about Hamming balls around F tilde and small dimensional affine subspaces. No, so this result of Guruswami will not hold for every code. But if you knew this for any other code, then you can do this. So in fact, you can replace this dimension k minus 1 by any d, and you'll get analogously k plus 1 to the d. You can even think of this dimension as n in the worst case. And then you get something better than q to the n sometimes, if q is very large. Okay. But this still does not improve on the existing parameters. It gives a simplified proof of 1 over epsilon to the 1 over epsilon. What we want to do is get a poly 1 over epsilon kind of bound. And that would be round 4. So now we are going to use the folded structure of Reed-Solomon. So until now, everything was just linear codes and affine subspaces. And we'll prove a bound of k minus 1 d plus 1. So the dependence on d is going to become linear from exponential. Okay. What we were really using was that as soon as a coordinate was an agreement, there is a new affine constraint, and the ambient search space went from dimension d to d minus 1. And that's how the induction proceeded. In the folded Reed-Solomon codes, each coordinate being an agreement actually gives you multiple affine constraints. Because each coordinate being an agreement actually gives us, in the best case, would give m linearly independent constraints. So we can hope to go from d to much lower. If we could always go from d to 0, that would again give the disjointness property of agreement sets, and we'll get optimal list sizes. Unfortunately, we are not able to show that this is always the case, that we can go from d to 0. But what value we get instead of 0 here is basically the rank of the linear system that involves T1 to TD. Previously, it was just one constraint. Now it will see some matrix there, and it depends on the rank of that matrix. In general, let's say we go from D to D sub j. This was a result proved already by Guruswami Kopati in a different context, where they say, let's say the jth coordinate being an agreement takes dimension d to dj, then on average we can say that this dimension is going to be small. Might not be true for every j, but overall this is going to be like a constant fraction small. Okay. So the smaller dj is, the better list sizes we can use, because dj is the new dimension we get when fixing a coordinate. And with this, we can essentially prove the statement that we are after. We'll not be able to go into the full proof, but let me give you some ideas about how this. Okay. So how do we obtain this linear dependence on D? Well, for now, let me lie. Let's just say we are looking for k minus 1 D. Then really what is going on is we sum up everything in the list. Each list code word is going to agree in at least Rn positions, because uh, the decoding radius is always less than delta. If it was delta, we still agree with f tilde in Rn positions. It's always less than delta, so we do actually better. So the total amount of agreement, if we sum over all list code words, is going to be at least Rn times the size of list. From the other side, we can use induction hypothesis. That the jth guy is going to be in at most k minus 1 dj places, where dj is the new rank that we get, or the new dimension that we get. And using the average bound on dj, we can replace this by k minus 1 rd times n. This would directly give the size of list being k minus 1d. This is not real because the base case of the inductive hypothesis is already not. For d equal to 0, the list size we have is 1. For d equal to 1, we have list size of k, which is, okay, I guess that is still okay. But for the base case, this is not okay. And this is induction, so errors, even a little bit of error will accumulate. So the real version would have k minus 1 d plus 1. So this side would become larger. But actually, the left side also is a bit bigger, because Rn is just saying that we are okay with distance delta. The real distance is k over k plus 1, so some fraction away from delta. That gives us some edge over just R. It's really this weighted mean of 1 and R. It's a little bit more than R. And when we plug this in along with the plus 1, then with some algebraic manipulation, we eventually can get k minus 1 d plus 1. This is also with an asterisk. There are more things to take care of here. When dj is just d, we can't rely on induction hypothesis. But all of those things work out. Okay. Okay. To talk about this expected, the bound on expected dj, the main lemma that we use from the Guruswami-Kopati work is this thing called folded Wronskian determinant, and I wanted to show this in case it has some other applications also. So really the lemma says that if we have d polynomials and we write down this determinant, so the first row is all f1x, f2x, and so on. Second row is f1 gamma x, f2 gamma x, and so on. Likewise till f1 gamma to the d minus 1x, and so on. Then this is non-zero as a polynomial if and only if these guys are all linearly independent. One side is easy to see. If these are linearly dependent, then this is clearly 0 as a determinant. But the other side is also true. And these are the kind of matrices that pop up when we talk about agreement with folded Reed-Solomon codes, etc. So these were originally used for constructing subspace designs. Uh, and what we use is whenever DJ that we did not go from D to 0, we were stuck at some, let's say DJ equals 3, that would contribute some roots to this Wronskian determinant, a root with multiplicity dj. And overall, this is still a bounded degree polynomial. This is a polynomial with degree d times Rn, because Rn is each f1 through fd, and the size of this determinant is d cross d. So this would give a average case bound on expected dj. Again, this is pretty much the entire proof, if you're willing to take this lemma as written. There's some more details that need to be worked, but little d here as written, d can be anything. When we think of it, we are working with a d where we know the list is contained. Okay. Yes, yes, yes. And really, this matrix is going to be multiplied by the T1 through TD, the free parameters that we had in the list. So you multiply this entire matrix by a column vector that is T1 through TD. That's the new affine constraint that you get. On the other side, you'll have something depending on G. So the rank of this system gets related to the determinant. This is for, yes. Yeah, so gamma needs to be, I think just high order suffices. It doesn't need to be generator. But exactly how much high order, I think that should depend on degree. Yeah. So really, this black box is the use of why gamma works, this lemma. What we showed was that folded Reed-Solomon codes have very close to optimal list size. They're 1 over epsilon square. So in an independent work, Chen and Zhang actually showed that they have optimal size, 1 over epsilon, which is the best we can do. They use different techniques. They also use folded Wronskian determinant, but the rest of the techniques are quite different. I don't know if this technique can be extended to get this optimal list size or not. So the prior works that tried to reduce the list size actually came with a randomized algorithm, but it's not clear how to de-randomize that algorithm. So Guruswami's proof already gives a basis where the list is contained in quadratic time. That was recently made near linear time. But after that, pruning the subspace, which is essentially what this proof is doing, that pruning the subspace is not very good in terms of deterministic algorithms. In a randomized way, we can do it with random pinning of coordinates, but it's not clear how to do it in a deterministic. This folded Wronskian determinant is basically a new polynomial that is associated to every linear subspace. It's not a property of these polynomials, it's really a property of the subspace they are spanning up to constant. And it's like we are giving up more and more structure as more and more complicated affine subspaces we look at. So a dimension 2 affine subspace is going to be more structured, dimension 3 less structured, and so on. Can we generalize this to general linear codes? Can there be more applications of this? I think it's an interesting idea. And finally, as somebody asked, like for Reed-Solomon codes themselves, we know that randomly chosen evaluation points do very well in terms of list decoding capacity, but we still don't know an explicit evaluation set that will do well. And some of these ideas help with that. Thanks. Uh, so for efficient decoding, remember all of this is saying that once you have a constant dimensional subspace, after that you can reduce the list size further. So the most uh, obvious algorithm is that you get a basis of the subspace and then try out everything in the subspace. That's going to take something like n to the k time. That's still polynomial time. If you want to do better than that, in randomized algorithms, we can do it in n log n time overall. In deterministic, I think the best is still this n to the 1 over epsilon. We don't know of doing things better than that. The questions? Uh, I don't know. I think in PCPs, the idea would be to have more local algorithms. And here, everything tends to be global. Uh, so I don't know if there are direct connections to PCPs, this kind of global list decoding. Uh, yeah. There are no more questions. Sorry.